Now we're going to start to put some numbers to these vectors. So we're going to introduce this basis where it includes a j vector and an I vector. Now the j vector is a vector of length 1 in the vertical direction, and the I vector is a vector of length 1 in the horizontal direction. Now these are both called unit vectors because they have the length of 1. Now this basis is used to represent any vector you can make on the 2D plane. So if I have a vector like this going to the point 1, 2, this vector can be made by using one I vector and then two j vectors. So this point would correspond to the vector I plus 2j. Now it comes that any point on the Cartesian plane, given an x coordinate and a y coordinate, can be represented as the x coordinate times I plus the y coordinate times j. Now we're going to move on to column vector notation. So say we have this same point again, xi plus yj. Now the column vector is basically just placing these scalar components, so the x and the y, not the vector components, in a vertical stack like this. Right? So these two lines are identical. So the x just represents how far along the horizontal axis do you go, and the y says how far up or down do you go. So if I wanted to look at the vector 3, 2, this vector means go right 3, then up 2. Right 3, so 1, 2, 3, and then up 2. So all the way up to here. So the vector would be this. This is the vector 3, 2. Now remember, vectors can be anywhere. They don't have to start at the origin. They can start from anywhere, as long as it's go right 3 and up 2. Now negatives aren't much different. So say we have the vector minus 2, minus 1. Basically means go left 2. That's for the I component, and down 1. So the vector will be this. Now remember, a vector like this is also the same, and a vector like this is also the same vector. They're all minus 2, minus 1. It doesn't matter where they start. Now, adding vectors is now a lot easier than before, because now we actually have numbers to work with. So say we have a vector that's like 2, 3, and we want to add it to the vector minus 1 and 4. All you have to do is add the I components and add the j components. So this will be 2 minus 1, and then the second number will be 3 plus 4. And scalar multiplication is also done component-wise. So say you wanted to do 3 times a random vector, like minus 2 and 3. This is also the same as just timesing the 3 with each component. Now that we have numbers associated with vectors, we can also understand how to calculate the magnitude of a vector or the angle of a vector. Say we have a vector called u, and u is the vector x, y in column notation, meaning this point here is x, and this point over here is y. Now, if you have a keen eye, you can see that this is a right angle triangle. And so if you want to find the length of this side, or in other words, the magnitude of the vector, you can just do Pythagoras' theorem. So the hypotenuse squared equals the length of the other side squared. And so if you square root both sides, it has to be positive because it's a length. Squared plus y squared. And if you wanted to find any form of angle here, so we know that this length here is x and this length here is y, it's opposite and adjacent, so you're going to use tan. And so tan theta equals y on x, or theta equals the tan inverse of y on x. So we're going to go through a quick example here. So we have this triangle and 3 points represented as A, B, C. Now remember, these points correspond with a vector coming from the origin O. That's what this dotted line here is. I just drew a dotted line to represent the vector OB. Now a question is, find the vector AB. So the vector starting from the point A going to the point B. Now you could eyeball it in this case because I'm using gridded paper, it goes across 2 and up 1. So we are expecting the vector to be something along the lines of 2, 1. Right, but let's say you didn't have this grid or the diagram wasn't to scale. How would you do it? Now, there's a very, very important formula that is a lifesaver when it comes to questions like this. This also helps in physics. This formula is AB equals OB minus OA. This is just a time saver kind of formula. It'll save you so much time in an exam if you just remember this, but basically how this comes about is to get from A to B, we can go the path along minus A and then plus B. And minus A plus B is the same as saying B minus A or OB minus OA, right? And we want to find this in column vector form. So since these are all vectors, we need these arrows. Now the vector OB corresponds to this point here, which is 1, 2. And OA is minus 1 and 1. Now we just minus each component. So the first one will be 1 minus minus 1. So that's 2, because minus minus makes it a positive. And 2 minus 1 is 1. And so that's our answer for AB. Now for CB, you can tell it just goes directly up. There is no X component. So we're expecting a 0 in the first number, but you can see it goes up 3 boxes. So the answer should be 0, 3, just because I've drawn the diagram to scale, but you're not always going to get the diagram to scale. So if we just use our same formula again, CB equals OB minus OC, we can write these as column vectors. So OB is 1 and 2. And OC is 1 and minus 1. Now you just minus the components. So we have 1 minus 1, which is 0. Now we have 2 minus minus 1. So there's a double negative there, so it's an addition. So we have 0 and 2 minus minus 1, which is 3. And that's our answer for the question. So a follow-up question could be find the magnitude of AB and the magnitude of CB. So we have AB and CB there. So the magnitude of AB, if you remember our formula, is the square root of the x component squared, or the I component squared, so 2 squared, plus the j component squared. And this will be root 5. Now CB is the square root of 0 squared, the I component squared, plus the j component squared. Right, and this will be the square root of 9, which is just 3, and that's our answer. Thank you for watching this video on column vectors. I hope you do well in Math Extension 1.